In today's video, we are going to look at what's known as optimization problems. In an optimization problem, the idea is you're given a function, a quantity, that you wish to either minimize or maximize. So for example, you could be asked to minimize the total cost of something or to maximize the total profit of something. This video will only be examples, and you'll see the steps used to solve optimization problems as we work through these examples. For our first example, we're told that a homeowner has $320 to spend on building a fence around a rectangular garden. 3 sides of the fence will be constructed with wire fencing at a cost of $2 per linear foot. The fourth side will be constructed with wood fencing at a cost of $6 per linear foot. We are going to find the dimensions and the area of the largest garden that can be enclosed. All right, so the first thing is let's try and draw a picture. And so what we'll do is we'll say, okay, let the blue be what'll be $2 per linear foot. This will be the wire fencing. And we'll say the green is the wood fencing. And that should be good enough. All right, wire fencing is $2 per foot. Wood fencing is $6 per foot. Now let's introduce variables, so we'll say that's x, that's y, and that's y. Now the area is length times width, so it'll be x times y. Cost. So it's going to be $2 times x plus $2 times y plus $6 times x plus $2 times y. And so I just started and went around counterclockwise. This is a total of 8x plus 4y. And this has to be $320. This means that 4y is 320 minus 8x, or y itself is 80 minus 2x. We take this y, we'll plug it into the area, and we'll now have area strictly as a function of x times 80 minus 2x, which is 80x minus 2x squared. We now need to determine a domain. Well, first, we know that x must be greater than or equal to 0, right? It doesn't make sense to have a side that is negative length. Well, that means that y, which is 80 minus 2x, must also be greater than or equal to 0, and we can solve for x. And find that 40 is greater than or equal to x. So our domain is 0 less than or equal to x, less than or equal to 40. We wish to maximize this function. So to maximize it, first take a prime of x, that is 80 minus 4x. Set equal to 0 and solve. We'll have x is equal to 20. So that is the critical value for our area function. Now remember, extrema can only occur at the endpoints or at a critical point. To determine if this is going to be a min or a max, take a double prime of x, which is negative 4, which means that a double prime of 20 will be less than 0, which means 20 results in a max. Now there is a corollary to the second derivative test, which states that if c is the only critical value within the domain, then the second derivative test gives you an absolute extrema. So 20 is the only critical number within our domain 0 to 40. This means that not only is 20 a relative max, it is guaranteed to be an absolute max. So x equals 20 maximizes area. This means that y, which was 80 minus, was 80 minus 2x, is equal to 80 minus 40, which is 40. So the dimensions that maximize area are 20 feet by 40 feet, and the maximum area is 20 by 40, which is 800 square feet. For our second example, let's take a look. An office supply company sells X permanent markers per year at P dollars per marker. The price-demand equation for these markers is P equals 10 minus 0.001x. At what price should the company charge for the markers to maximize revenue? And then what is this maximum revenue? Well, we're told that the price per marker is 10 minus 0.001x. Now remember that revenue is the price charged per unit times the number of units sold. So this will be x times 10 minus 0.001x, or 10x minus 0.001x squared. Now, price must be greater than or equal to 0. So 10 minus 0.001x must be greater than or equal to 0. So 10 is larger than 0.001x, which means that x itself must be less than or equal to 10,000. Also, the number of units must be greater than 0. So our domain is 0 less than or equal to x, less than or equal to 10,000. Now, r prime will be 10 minus 0.002x. Set that equal to 0. 10 is 0.002x, which means x itself is 5,000. R double prime of x is negative 0.002, which means that r double prime of 5,000 will be less than 0, and so second derivative test says 5,000 results in a max. So 5,000 units maximizes revenue. So the price charged that maximizes revenue is P of 5,000. Right, that is 10 minus 0.001 times 5,000, which is equal to $5. The max revenue is that $5 times the 5,000 units sold, and this is $25,000. So if we charge a price of $5 per marker, we will maximize our revenue at $25,000. Now, let's take a look. When a management training company prices its seminar on management techniques at $400 per person, 1,000 people will attend the seminar. The company estimates that for each $5 reduction in price, an additional 20 people will attend. How much should the company charge for the seminar in order to maximize its revenue, and what will this maximum revenue be? Right, so P is going to represent the price. Well, it's $400 minus $5 deduction. So how many times we're reducing it by 5? That's what X represents, the number of reductions. Then those that attend, we'll call that C. Right? 1,000 people plus 20 times each $5 reduction. So X is number of $5 reductions. Well, revenue, again, is the price charged per unit times number of units sold. So this will be 400 minus 5x times 1,000 plus 20x, which equals 400,000 plus 8,000x minus 5,000x, so actually 3,000 plus 3,000x minus 100x squared. For the domain, again, we must have price larger than 0. So you'll find that x is less than or equal to 80. Domain will then be 0 less than or equal to x less than or equal to 80. And again, remember, x is the number of $5 reductions. R prime. 3,000 minus 200x equal to 0 and solve. We get that 3,000 would equal 200x, or that x itself is equal to 15. Our double prime of x is simply negative 200, which means that our double prime of that 15 is less than 0, which means 15 results in a max by the second derivative test. So the company should charge $400 minus 15 $5 reductions. which is $325. Max revenue would then be R of 15, which winds up being $422,500. So to maximize revenue, the company should charge $325 per person to attend the seminar, and the revenue that will be earned will be about $422,500. And as our final example in this video, a multimedia company anticipates that there will be a demand for 20,000 copies of a certain DVD during the next year. It costs the company 50 cents to store a DVD for 1 year. Each time it must make additional DVDs, it costs $200 to set up the equipment. How many DVDs should the company make during each production run to minimize its total storage and setup costs? We'll say X will be the number of DVDs manufactured per run, and we'll let Y be the number of production runs. Now, cost for setup, or setup cost, I'd rather call it that, this is simple. It's $200 times the number of runs. Now, number of DVDs in storage. This will go from X down to 0, right? So we produce X DVDs. They're being stored. As they sell, that will drop down to 0, and then we have our next production run, which brings in another X. Right, this averages X over 2 DVDs in storage per day. Therefore, the cost of storage, the storage cost, is 50 cents times X over 2, which is 0.25 times X. Now, total cost. Is setup cost plus storage cost. We also know that X times Y has to be 20,000, right? Since the company is anticipating 20,000 copies of demand, then that's the maximum number that we should produce. Solving for Y, we get 20,000 divided by X. So I shouldn't call that C of X, that's just C. So C of X will be 200 times 20,000 over X plus 0.25X. So this is 400,000 divided by X plus 0.25X. We also know the domain. Right, we'll obviously produce a minimum of 1 DVD per production run. And the maximum we produce is 20,000. Right, so we could do 20,000 production runs of 1 DVD each, or a single production run of 20,000 DVDs. C prime. For negative 400,000 over x squared plus 0.25. Rewrite this as negative 400,000 plus 0.25 x squared all over x squared. Now this would be undefined at 0, but 0 is not in our domain, so we can ignore it. So we set this equal to 0 and we solve. This means that negative 400,000 plus 0.25 x squared is equal to 0, or 0.25 x squared is equal to 400,000. This would mean that x squared is equal to 16 million, and x would be the square root of that, which is 4,000. Again, x must be positive, so we can ignore the negative 4,000. C double prime of x is positive 8 million I apologize. This should not have been 400,000. This should have been 4 million. And everything else is right. So 8 million over x cubed. If we plug in 4,000, we're going to get greater than 0. 4,000 cubed is a number larger than 0. This means that 4,000 results in a min by the second derivative test. So the company minimizes total cost by producing company minimizes total cost by producing 4,000 DVDs 5 times during the year. Right, this type of problem is known as an inventory control problem. All right, and that concludes this video on optimization problems. The next video in this lecture series will start the study of integration. So, I will see you all in the next video.